Welcome to Derictronic, where we experiment, learn, and build with electronics. Today, we will be building a voltage regulator circuit that contains a component known as a Zener diode. Let us first compare the Zener diode from the rectifier diodes we saw in our previous video. When connected in forward bias, the Zener diode will operate similar to a rectifier diode. In reverse bias, similar to the rectifier diode, it will allow very little current to flow through it for as long as the voltage across the Zener diode is less than its reverse breakdown voltage. We will take a closer look at what that reverse breakdown voltage is later on. However, when the voltage on the Zener diode, while connected in reverse bias, exceeds its reverse breakdown voltage, the Zener diode now is acting like a voltage regulator. A voltage regulator, by the way, is a circuitry that will keep the voltage on the output stable even if there are significant fluctuations on the input voltage. Such type of circuitry is critical for the protection of loads connected on an outlet from unwanted fluctuations from the power source. Now, before we construct or see the actual circuitry of a voltage regulator, let's take a look at what the Zener diode looks like. Now, in electrical schematic diagram, the Zener diode would look like this, represented by this symbol. So it's similar to the ordinary rectifier diode. Its cathode is drawn in this manner. Okay. Now, the actual look of the Zener diode would have something like this at the bottom. It will normally be enclosed in a red casing with a black stripe marking its cathode. What we see right here is the voltage current characteristic curves of the Zener diode. At the upper right hand portion, this one shows the relationship of the forward bias voltage of the diode with its forward current. At the lower left hand portion here, this curve shows the relationship between the reverse bias voltage of the diode with its reverse current. Now, given that in forward bias, the Zener diode is similar to the rectifier diode, and we need to connect the Zener diode in reverse bias so as to take advantage of its voltage regulation capabilities, I would like to concentrate my discussion on this curve, reverse bias, at the reverse bias. Now, as mentioned earlier, to understand this curve, we need to have a closer look at the reverse breakdown voltage of the Zener diode, which is represented here as V sub Z. Now, as mentioned earlier, when the voltage across the diode is less than its Zener voltage, there's very little current flowing through it, as you can see here. That operation or that characteristic is similar to a rectifier diode. However, when the voltage on the Zener diode exceeds that reverse breakdown voltage, it is now operating like a voltage regulator. To further understand that, let's take a look at this shaded area I marked here. As you can see in that shaded area, even if the current goes up rapidly, which normally happens when there are voltage fluctuations at the source input or the input voltage, the voltage across the diode remains stable. Now, the operating region of the Zener diode is marked here in this graph also, the breakdown region here. Now, you can see here that there's a minimum allowed Zener current and a maximum allowed Zener current across the diode. Now, we don't want the current across the diode to go over this IZ max or the maximum allowable Zener current, because when that happens, the diode would most probably get damaged. Now, let's take a look at the voltage regulator circuit we will be constructing in this video. That circuit would look like this. Now, for our power source, we will be needing a variable DC supply, as you see here on the left. Connected on the positive side of that power supply is a resistor here. That resistor I would like to call as a limiting resistor. See there. Now, the job of this resistor is to limit the current flowing through this branch. Now, at the end, we have a load resistor there, R2. Now, we could take a look at this load resistor as something like an equipment or a device that you plug at the end of a circuit. So that can be anything. That can be a refrigerator, a television, a laptop, a tablet, or whatever. Now, the Zener diode, as you see here, will be connected in parallel with our load. Another interesting thing that you might want to take a look at here or notice here is that the Zener diode is in reverse bias. Its anode is connected to ground, while its cathode here at the top is connected to the positive terminal of the voltage source. Now, what will happen in this demo is that we will first set the voltage source here to a low value, let's say 1 volt. Then we will gradually increase it, let's say 2, 3, 4 increments of 1 volt, up to 10 volts maybe. At each pass, we will be measuring two things in this circuit. First one is the load voltage or the voltage on R2, across R2. Now, before I go to the second one there, okay, maybe it's interesting to note that the voltage across R2, given that R2 is in parallel with the Zener diode, so the voltage across this resistor, the load resistor, is also the voltage across this diode. So whenever I say voltage across the load, it is also the same as saying that it's also the voltage across the Zener diode. Now, the second thing that we need to measure in this circuit is the current flowing through the Zener diode there, I sub Z. Now, as we saw earlier, that I sub Z should not increase a maximum value. Meaning, once that I sub Z goes over that maximum value, the Zener diode gets damaged.
Now, before we construct the voltage regulator circuit, let us first determine the reverse breakdown voltage of the Zener diode we will be using. We will be utilizing this Finersi LCRP1 component tester for that purpose. Now, as mentioned earlier, a Zener diode would most probably look something like this. It's enclosed in a red casing, as you can see here, with its cathode marked with the black stripe. So the cathode, the black stripe is here on the left. So the left side is the cathode, the right side is its anode. Now, to get the reverse breakdown voltage of this Zener diode, let's make use of this component tester, the Finersi LCRP1. Let's connect it first. So I will be connecting the cathode here and the anode on the other side, like that. Now, by the way, this LCRP1 of Finersi was initially advertised as a transistor tester, but we could also use it for Zener diode. It's quite handy. Let's turn this on. Okay, set to Zener, and let's test. Okay, there. Okay, because you see on the value there shown on the screen, the reverse breakdown the voltage of this diode that we will be using in the circuit is 3.15 volts. So it's somewhere between 3.1 to 3.2 volts in terms of value. Let's have that in mind as we construct our video and see the results later on when we connect the multimeters. To construct our voltage regulator circuit, we will be using this COM3 Lab proto board, just like in our previous video. For our power source, we have to set the function generator of this proto board to measure DC voltage and connect our power source from here. A closer look at that be something like this, guys. So the positive of our power source will be connected here at U+, while the negative of our power source will be connected here at ground. Now, the positive of U plus, this jumper wire, will have to be connected to, as you could, if you could remember on the schematic diagram shown earlier in the video, will have to be connected to the 100 ohm resistor. This here at the top is our 100 ohm resistor. I will now connect the positive of our power supply to the 100 ohm resistor, to one of the legs of the 100 ohm resistor, like so. There. Now, the negative for power supply, this one, the ground, will have to be connected to, maybe to the power rail. I'll connect it to the power rail. I'm going to use the blue power rail here at the bottom. Like so. A closer look at that would look something like this. Here at the top, you can see the connection of the red or the positive power source, the positive terminal for power source. And near the bottom, you can see the ground connected to the power rail. Now notice that our Zener diode here, the anode side of our Zener diode is connected to ground also. And one of the leg of our load resistor, here's our load resistor, the blue resistor here. This is the 1 kilo ohm resistor. Is also connected to the ground terminal of our power source. As similar, that will be similar to the schematic diagram we saw earlier. Now, the load resistor will have to be connected to the other leg of that 100 ohm resistor at the top, our limiting resistor. Let's do that now. So I'll connect the load resistor here. Maybe somewhere there. And our Zener diode, the anode side of our Zener diode, the cathode side of our Zener diode will also have to be connected on that line or on that leg of that limiting resistor. There. Now, once that is done, our circuit, our voltage regulator circuit is more or less complete. As mentioned previously, what we will be doing here is that we will first set our variable DC supply voltage to a low value first, maybe 1 volt, and we will gradually increase it maybe by increments of 1 volt until about 10 volts. And for each pass, we will be measuring two things on this circuit. First is the voltage across our load resistor here. And second, the current flowing through our Zener diode here. Now, in order to do that, we will be using the multimeters of this COM3 Lab protoboard, which you will see somewhere here at the top. Now, we have two multimeters here, as mentioned in the previous video. We have here multimeter 1 and multimeter 2. Now, what we will do here is we're going to use multimeter 1 to measure the voltage across the load resistor, and we're going to make use of multimeter 2 to measure the current flowing through our Zener diode. In order to do that, we need some more jumper wires. First, let's connect the wires for multimeter 1, which we will use to measure the voltage across our load resistor. If that's the case, I need to put one wire here at V and another wire here at COM, multimeter 1. So V and COM. Now, the red wire, or the one connected at V, which is the positive terminal of our multimeter number 1, will have to be connected maybe here, somewhere here at the top of the resistor, the top leg of the resistor. I'll connect it here. Let me just transfer this one somewhere here. I'll connect it here at the top. Just transfer the jumper wire, the yellow jumper wire first. Okay, there. C. Okay. Well, the COM will have to be connected to the other leg. Since the other leg is connected to the blue power rail, the bottom blue power rail, I can also connect this wire, the COM wire of our multimeter 1, to the bottom blue power rail also. As you can see there. That will measure the voltage across the load resistor. Now, As for multimeter number 2, which we will use to measure the current flowing through the Zener diode, okay, what I need to do first is I will remove this green wire, because in order to measure current, we need to connect multimeter 2 in series with the Zener diode. Okay, in order to do that, I need to remove first the green wire here, the green jumper wire here, and replace it with a connection coming from multimeter number 2. How do you do that? Let's remove the green jumper wire first. Put it aside. Then we will connect our jumper wires on multimeter number 2. Since we will be measuring current, I will be putting the red wire, a red wire on A, as you can see there, and a black wire on COM, as you see there. Now, to put multimeter 2 in series with our Zener diode here at the bottom, what I need to do is this. The red wire, or the positive wire, the positive terminal of our multimeter 2 will have to be connected here on the right leg of resistor 1, and the negative terminal, or the COM terminal of multimeter 2 will have to be connected to the cathode of the Zener diode. Somewhere here. Now, a closer look of that would be something like this. Connection on multimeter number 2. Now, what will happen here, the current that will be coming from the source will first pass through our limiting resistor here, and once the current goes or exits the second leg, the other leg, that current will pass through this wire, going through multimeter number 2, and come out of the black wire, coming out of multimeter 2, and then eventually passes through our Zener diode. That's what I meant earlier of putting multimeter 2 in series with our Zener diode. So the connection you see here more or less completes the connection of our multimeters 1 and 2. Just kindly remember that multimeter 1 is measuring the voltage across our load resistor, and multimeter number 2 is measuring the current flowing through our Zener diode. Now, we need to turn on, at this point, the COM3 lab, two switches, one here at the top first, like that, here. And we have to also switch on there. We also need to switch on the function generator, or the DC supply here at the bottom, because there's a separate switch here, like so. So you need to see that light here. And once that is done, we will now use, at this point, we will now use the COM3 Lab companion software to manipulate the voltages across, or the voltage across, the voltage coming out of the source, and take the readings from our meters. See here. Here's the COM3 Lab companion software. So first, let's set the function generator to measure DC supply voltage. We do it like this. Function generator set to DC here, straight line. Okay. Then we will initially set the voltage to 1 volt. 1 volt DC. There. So our function generator is initially set to 1 volts DC. As you can see right there. Now, for the multimeters, let's open both. This is multimeter 1. See here. And this is multimeter 2. See here. Now, our multimeter has 5 modes. If you take a look at here, multimeter 1 on the left, I will show you all the 5 modes. Okay. The first mode is voltage DC. If I click letter M, you will see the second mode. This is voltage AC. If I click letter M again, you see the third mode. This is current DC, or direct current. If I click M again, you will see the next, or the fourth mode, which is current AC, or alternating current. Then, if I click it again, you see mode number 5, That's resistance in ohms. So what we need to do here is this. I would need to set multimeter 1 to measure DC voltage, mode number 1, and set multimeter 2 to measure direct current, which is mode number 3. There. So multimeter 1 will show the value of the voltage across the load, which interestingly enough is also the voltage across the diode. And multimeter number 2 will show the Zener current, or the current flowing through our Zener diode. Now, right now, voltage across, or the voltage source is set to 1 volt. So at 1 volt, the voltage across the diode is 0.913 volts, and the voltage and the current across the going through the Zener diode is 0. Actually, we have a very low current passing through the diode. Remember that our diode is in reverse bias, and if the voltage across the diode, as you see here, 0.913, is less than the reverse breakdown voltage, which you saw earlier, around 3.1 volts. If the voltage across the diode is less than 3.1 volts, or the diode we're using, okay, the diode is in reverse bias, and in that case, the current flowing through it would be very small. So as you can see it right here. Maybe this will be most probably in nanoamperes. That's why the multimeter 2 right now cannot display the value. Now, let's increase the voltage on the source. I'll make it 2 volts. Enter. You can see now the voltage on the across the load increased proportionally, became 1.8 volts. So from 0.9 to 1.8. And the Zener current is still very small. Why? Because the diode is still in reverse bias, and the voltage across the Zener diode is still less than the reverse breakdown voltage. Now, let's increase it to 3 volts. Now, okay, now we're seeing some voltage on the, some current flowing through the diode already. And the voltage across the load is now at 2.64. 3 volts on the source and 2.64 on the load. Now, this voltage is also the voltage across the diode. Now, we're seeing some 0.9 milliampere current flowing through the diode now. Why is this so? Because the voltage across the diode now is nearing the reverse breakdown voltage. Now, we're seeing some small current flowing through the Zener diode. It's still very small at microamperes, 900 microamperes. Let's increase the voltage some more, 4 volts. Now, see right here, the voltage across the load is now 3.21 volts. Same voltage across the diode. Now, the diode current, or the Zener current, Zener diode current, is now at 4.6 milliamperes. That's a significant value for the current now. It's in milliamperes now. Now, why is that so? Because at this point, the voltage across the Zener diode exceeds the reverse breakdown voltage, exceeds its reverse breakdown voltage now. So now we have a significant current flowing through the diode at this point. Now, as we now increase the voltage on the source further, 5 volts, we will see something interesting happen. Take a look at the increase of the voltage on the load. Earlier, the increase was proportional to the increase of the voltage on the source. However, now, when I change from 4 to 5, the increase from 4 volts to 5 volts on the source, the increase of the voltage on the load is actually less than 0.2 volts. Now, if I increase it further, you will see that the voltage across, now it's 6, it's only 3.73. If I increase it to 7, the voltage across the load, 3.86. If I increase to 8, voltage across the load, 3.94. Increase to 9, voltage across the load, 4. Around 3.99, 4 volts across the load. Highest setting, 10 volts on the source. It's a little over 4 volts, 4.03 volts on the load. As you can see from there, okay, the current is increasing rapidly. as I increase the voltage from 4 to 10. However, the voltage across the load is just increasing minimally, or is actually stable at this point, starting at 4 volts. Why? Because at 4 volts, see here, the voltage across the load has already exceeded the reverse breakdown voltage of our Zener diode.
Let us now analyze the data we saw earlier. To easily understand the readings we saw on the demo, what I did here is that I plotted the readings of the source voltage, load voltage, and Zener current in a line graph, as you can see here. This particular graph on the left shows the relationship between the source voltage, which I plotted here on the horizontal axis of the graph, with that of the load voltage, which I plotted here on the vertical axis of the graph. As you can see here in this graph, when the source voltage was increased from 0 to 4 volts, there was a more or less proportional increase also on the load voltage, about a 3.2, 3.3 volt increase on the load voltage. However, when the source voltage was increased from 4 to 10 volts, the increase on the load voltage became less. Based on that shaded area, you see here, the increase was less than 1 volt, which is quite interesting. Now, what's the reason behind this? When we took that component tester earlier in the video and tried to take a look at the reverse breakdown voltage of the Zener diode we have on the circuit, we came out with this value, that the reverse breakdown voltage of that Zener diode we use is approximately equal to about 3.1 volts. Now, we can see that here in this graph. At 4 volts, source voltage at 4 volts, the value of the load voltage is around 3.2, 3.3 volts. And that value is now over, or have exceeded, the reverse breakdown voltage of the Zener diode. And that means, beyond that, the Zener diode is now acting like a voltage regulator. And that's clearly shown on this graph. Now, as a second analysis, we can take a look at now the relationship between the load voltage and the Zener current. The load voltage is plotted here on the horizontal axis of the graph. It's in volts, while the Zener current is plotted here on the vertical axis on this graph, which is measured in milliamperes. Now, as you can see here in this line graph, okay, just before, when the load voltage is less than 3.1 volts, the reverse breakdown voltage, so around here, there was very little current passing through the diode. So it's an ordinary diode, as mentioned earlier. It's an ordinary diode in reverse bias when the voltage on the diode is less than the reverse breakdown voltage. However, when the voltage on the diode goes over the reverse breakdown voltage, as you can see in the graph here, the current increases rapidly. Now, an increase in current like that normally happens when there are voltage fluctuations on the input. Now, as you can see here, that even if the current is increasing rapidly, the voltage across the diode remains fairly stable. Hence, the diode now, at this stage, is regulating the voltage across the load. With that, I would like to conclude the video for today. And as always, I would like to encourage everybody to keep experimenting, keep learning, and hope to see you next time here in Derricktronic.